Good morning, everyone. Welcome to the next lecture. In the last lecture, we discussed the arithmetic progression and also explained how to find the nth term of an arithmetic progression and the sum of n terms in an arithmetic progression. Today, we will discuss the geometric progression. See, in the last lecture, we defined the arithmetic sequence is a special order in which the difference between any two consecutive terms is constant. We shall now move on to the other type of sequence we want to explore. See, consider one example 2, 6, 18, 54. Here each term in the sequence is 3 times previous terms. In the similar way, another sequence, see 1 minus 2, 4 minus 8. Each term here is minus 2 times the previous term. Such a sequence is generally called the geometric progression. And see, the geometric progression is the list of terms where the ratio of successive term is constant. Or it is the sequence in which any element after first is obtained by multiplying the previous element by a constant. As against the arithmetic progression, see, there is no common difference in the geometric progression. Instead of that, we are using a common ratio, which is the ratio of successive terms, which is always constant. And this common ratio is generally denoted by a small letter r. See, now we have a given example of a series that is 1, 2, 4, 8, 16, 32. And in this series, it is generally known as it is geometric progression. Why it is so? Because we will check it. The first term of this particular series is 1. We are denoting the first term is an initial term that is denoting in terms of a, which is equal to 1. And the common ratio here, see, we are denoting in terms of r, that is the ratio between two successive terms. See here, this is a1, a2, a3, a4. So here a2 divided by a1, that is the ratio between two successive terms should be constant. So we are taking the ratio between two terms, that is a2 divided by a1. So here a2 is equal to 2 divided by a1, which is equal to 1. So it is equal to 2. So 2 divided by 1, which is equal to 2. Similarly, take the ratio of another two consecutive terms, that is a3 and a2. See here a3 is equal to 4. So we can write it is 4 divided by a2, which is equal to 2. So 4 divided by 2, which is 2. Similarly, the ratio of two successive terms, that is 8 divided by 4, which is also equal to 2. So here we can say that the common ratio, that is r, which is obtained by dividing a term with its previous one. And this ratio of successive terms, here it is constant. See here, r is equal to 2, here also 2, here also 2. So we can say that the ratio of successive terms is constant, which is 2 in this particular case. Such a type of series is generally known as it is geometric progression. Now let us check another example. Check whether the given sequence, that is 9, 3, 1, 1 by 3, 1 by 9 is a geometric progression. So here we want to find out whether the given sequence is geometric progression or not. Here see the first term, that is a1, it is 9, a2 is 3 and so on. We can say that this is a3 is equal to 1, a4 is equal to 1 by 3, 9. So here we will check it the common ratio in the sense that if the common ratio is remaining constant throughout the successive terms, then we can say that this is a geometric progression. So consider here a is equal to 9 and we are going to find the common ratio, that is R. So which is equal to A2 divided by A1. So here A2 is equal to 3 divided by 9. We can say that it is 1 by 3. Consider another two successive terms, that is 1 by 3. A3 here it is 1 by 3, which is equal to again 1 by 3. Consider another two terms, that is 1 by 3 divided by 1, which is also equal to the 1 by 3. So in this particular case, the ratio of successive term is constant. That is common ratio here 1 by 3. In this case also 1 by 3. Here also 1 by 3. So we can say that the given sequence is a geometric progression. Now consider another one, the general form of a geometric progression. What actually the general form of a geometric progression? See, the first term is generally denoted in terms of A1, that is A1 is equal to A. The second term we are getting by multiplying the common ratio with the first term. So A2 is equal to A1 into R. We can write it is AR. The third term is equal to A3, which is A2 into R. That is A1 R into R. We can say that it is AR square. Similarly, the fourth term, which is A3, the third term into R. So it is A2 R square, or we can simply say that it is AR cube. So if you go for writing the nth term of an geometric progression, then we can say that the first term is equal to A, the second term is AR, third term is equal to AR square, fourth term is equal to AR cube, and the nth term, therefore here it is AR n raised to the power minus 1. So the nth term of a geometric progression is nothing but it is AR n minus 1, AR raised to the n minus 1. So here AR raised to the n minus 1, we can, by using this particular formula, we can find the nth term of a geometric progression. See here, what is an? This is nth term. And A is the initial term, or it is the first term. R is the common ratio, and n minus 1 is the term position. N minus 1 is the term position. So by using this particular formula, we can find the nth term of a geometric progression. Consider one example. Write down first 5 terms of a geometric progression which has the first term of 1 and the common ratio of 1 by 2. See here, we can find the nth term of an geometric progression by using the equation, that is an, that is nth term is equal to AR raised to the power n minus 1. So here the first term is equal to 1. So second term we can find the first term into the common ratio. What is common ratio? It is 1 by 2. So 1 into 1 by 2, which is equal to 1 by 2. The third term, that is AR square, or we can also say that AR into R. What is AR? That is the second term, that is half, that is 1 by 2 into 1 by 2, which is equal to 1 by 4. The fourth term is equal to AR cube. We can write it is AR square into R. What is AR square? It is 1 by 4 into R, which is 1 by 2. So it is equal to 1 by 8. Similarly, we can also find the fifth term, that is A5, which is equal to AR raised to the power 4, which we can calculate by using AR cube into R. What is AR cube here? Which is 1 by 8 into R, that is 1 by 2. So here it is 1 by 16. So the first 5 terms of a geometric progression here, by giving the first term is equal to 1 and the common ratio of 1 by 2, then the sequence are 1, 1 by 2, 1 by 4, 1 by 8, 1 by 6, 1 by 16. It is 1 by 16 and so on. Now consider another example. In a geometric progression, 10, 30, 90, and we want to find out the 4th and 10th term of this particular geometric progression. See, the nth term of a geometric progression we can find by using AR raised to the power n minus 1. A is given here, which is equal to first term, that is 10. R is equal to 30 divided by 10. That is the ratio of 2 consecutive terms. So 30 divided by 10, which is equal to 3. Then nth term is equal to AR raised to the power n minus 1. Now we can find A4, that is the 4th term, that is 10 into, that is a into 3 raised to the power r, which is equal to 3. So it is 3 raised to the power n, which is 4 minus 1, which is equal to 10 into 4 minus 1, which is cube. So 3 cube. So 10 into 3 cube, which is equal to 27, which is 10 into 27, which is equal to 270. So the fourth term of this given geometric progression is 270. Similarly, we also want to find out the 10th term. See, the 10th term of this given geometric progression is, it is 10 into 3 into, that is common ratio, that is r, raised to the power 10th term we want to find out. So it is 10 minus 1. If you go for simplifying it, then 10 into 3 raised to the power 9. See, 10 into 3 raised to the power 9, which is equal to 19,683. So here if you go for multiplying it, 1,96,830. This is the answer. That is the 10th term of this given geometric progression is 1,96,830. Now consider another example. We want to find out the terms in the geometric progression where 6, 12, 24 up to 1536. See here what are the information given. The a, first term is given, a which is equal to 6. The r common ratio, which is equal to the ratio of two consecutive numbers, that is 12 divided by 6, which is equal to 2. Then a n is also given, that is 1536. So we want to find out the number of terms in this particular geometric progression. See here, we can find out the nth term of an arithmetic geometric progression, which is equal to ar raised to the power n minus 1. Now we can substitute all these values here on this given formula. Then we will get an is equal to 1536, which is equal to a, that is 6 into 2 into, that is common ratio, raised to the power n minus 1. We don't know what actually the n is. We want to find out n. So we can simplify it. 1536, which is equal to 6 into 2 raised to the power n minus 1. See, I am taking this 6 into the denominator side, so it will be cancelled out here. It is wrongly written again here. We are going to divide the both side of the equation by using 6. Then it will become 1536 divided by 6, which is equal to 2 raised to the power n minus 1. This 6 is wrongly written. This is not here. It is 2 raised to the power n minus 1. So 1536 divided by 6, which is equal to 256, which is equal to 2 raised to the power n minus 1. Now we can write the 256 as a base of 2, which is equal to 2 raised to the power 8. We can write the 256 as a base of 2, then we can write it is 2 raised to the power 8, which is equal to 2 raised to the power n minus 1. Since see here, the base are same here, the exponent must be equal. We can equate the exponents. So 8 is equal to n minus 1. N minus 1 is equal to 8. Then what is n? N is equal to 9. That is 8 plus 1, which is equal to 9. So 1536 is nothing but it is the 9th term of this geometric progression. Now consider another one. How many terms are there in the geometric progression? 2, 4, 8 up to 126. See here, a is 2, r is 4 divided by 2, which is equal to 2, and an is equal to 128. The nth term we can find, that is ar raised to the power n minus 1. We are just substituting these values into the given formula. It will become 128, which is equal to 2 into 2 raised to the power n minus 1. So it will become, I am going to divide the both side of the equation by using 2. Then it will become, see, 128 divided by 2. I am taking this 2 into the denominator side, so it will become 128 divided by 2. Then 2n raised to the power n. What is remaining here? It is 2 raised to the power n minus 1. 128 divided by 2, which is equal to 64, which is equal to 2 raised to the power n minus 1. Again, here the base is 2. Here the 64 can be write as a base of 2. So which can be right, it is 2 raised to the power 6, which is equal to 2 raised to the power n minus 1. So since we have the same base here, that is 2, the exponent can be equal, or we can equate the exponents here. So we can say that it is n minus 1 is equal to 6, n is equal to, which is 6 plus 1, which is equal to 7. So 128 is the 7th term of a given geometric progression. Now consider another example. In a geometric progression, the 3rd term is 24 and the 6th term is 192. We want to find out the 10th term. We don't know what actually the first term and the common ratio. But at the same time, the 3rd term and the 6th term is given. So with the given information, see, we know the nth term is equal to the ar raised to the power n minus 1. So here the 3rd term we can write it is a3, which is equal to ar raised to the power 3 minus 1, which is equal to 24, because the 3rd term we are given here, it is 24. So we can simplify it is ar square. This is ar square is equal to 24. I am just denoting it is equation number 1. So similarly, the another information given here, it is 6th term is 192. So a6 is equal to a into r raised to the power 6 minus 1, which is 192. We can simplify it is ar raised to the power 5, that is 6 minus 1, which is equal to 5, which is equal to 192. I am denoting this is equation number 2. Now dividing the equation number 2 by using equation number 1, then it will become, see, this is equation number 2, that is ar raised to the power 5, which is equal to 192, and the equation number 1 is equal to ar square. See here, the a will be cancelled out, then r raised to the power 5 and r raised to the power 2. See here, exponent rule can be applied. So we can say that here r raised to the power 5 minus 2, this denominator exponents will be goes to the numerator and it will become minus sign. So it is r raised to the power 5 minus 2, which is equal to 192 divided by 24. So here 5 minus 2, that is r cube, which is equal to 192 divided by 24, which is 8. So r cube, see, we can say that it is, we can rewrite it is 2 cube. Since the exponents are same, we can simply say that r is equal to 2. That is common ratio, here it is 2. Now we know the r is equal to 2. We can substitute in any one of these equations. We are just substituting in the equation number 1. Then see here, the 3rd term, that is ar square, which is equal to 24. So we know what is r. We are just substituting here r is equal to 2. Then a into r 2 square, which is equal to 24. So it is 4a, which is equal to 24. Dividing the both side of the equation by using 4, then we can say that it is 24 divided by 4, which is 6. So first term of this geometric progression is equal to 6. Now we know the first term and the common ratio. Then we can substitute in the nth term of an geometric progression. So we know the 10th term we want to find out. So here a10, which is equal to ar raised to the power n minus 1, that is 6 into 2 raised to the power 10 minus 1, which is equal to 6 into 2 raised to the power 9. We can simplify it, 6 into 2 raised to the power 9, which is 512. And if you go for multiplying these two terms, it is equal to 3072. So the 10th term here, it is 3072. Now we are going to find the sum of n terms in a geometric progression. Suppose we want to find out the sum of first n terms in the geometric progression, then we will get in the geometric progression as that is sum, that is Sn is equal to the first term plus the second term, that is ar plus the third term, that is ar square plus ar cube up to ar raised to the power n minus 1. So here if the starting value is a and the common ratio is r, then we can use the symbol formula, that is the sum is equal to a into 1 minus r raised to the power n divided by 1 by r. By using this particular formula, we can find the sum of n terms in a geometric progression. Let us consider one example. Find the sum of first 4 terms in the series 10, 30, 90, 270. The 4 terms are given here and we want to find out the sum. Either we have to add these 4 terms, but if your number of sequence is very large, then it is very difficult to find the sum of this given geometric progression. So we can use this particular formula. Here A is equal to 10, R is equal to 30 divided by 10, which is equal to 3, and N, that is nth term, see 4 terms are there, so N is equal to 4. The sum formula is given here, that is A into 1 minus R raised to the power N divided by 1 minus R, see, which is equal to 10 into 1 minus 3 raised to the power 4 divided by 1 minus 3. If you go for simplifying it, then 10 into 1 minus 3 raised to the power 4, which is equal to 81 divided by 1 minus 3, then 10 into minus 80, 1 minus 81, it is minus 80. Then if you go for simplifying it, it is minus 800 divided by minus 2, which is equal to 400. Now another example, find the sum of geometric series, that is 2, 6, 18, 54, where there are 6 terms in the series. So here we want to find out the sum of 6 terms in the given geometric series. Here A is given 2, R is equal to 6 divided by 2, which is equal to 3, N is equal to 6. Now we can use the formula of sum, that is A into 1 minus R raised to the power N divided by 1 minus R. We can substitute all these values here, then it will become 2 into 1 minus 3 raised to the power 6 divided by 1 minus 3. We can simplify it, 2 into 1 minus 3 raised to the power 6, which is 729 divided by 1 minus 3. Then 2 into 1 minus 729, which is equal to minus 728 divided by 1 minus 3. Then if you multiply these two terms, then minus 1456 divided by 1 minus 3, which is equal to minus 2, which is 728. So the sum of 6 terms in this given series is 728. Now another example, see here how many terms of the geometric progression. Here it is, progression is given 64, 32, 16, has the sum 127 1 by 2. See here the first term is 64, R is equal to 32 divided by 64, which is equal to 1 by 2. Then here the Sn, the sum of n terms are given here, that is 127 into 1 by 2. See, 127 into 1 by 2 we can write, or we can convert this mixed term, that is 127 into 1 by 2, to a improper function. We can multiply this 127 by the denominator 2 of the fraction and then add the numerator fraction. So 127 into 2 plus 1, which is equal to 255 divided by 2. So we can rewrite this is 255 divided by 2. Now we can use the sum formula, that is A into 1 minus R raised to the power N divided by 1 minus R. See here, Sn is equal to 255 divided by 2, A is equal to 64, 1 minus R, which is 1 by 2 raised to the power N, which we want to find out here, divided by 1 minus 1 by 2. See here we can simplify it. I am taking just rearranging this particular equation by taking 255 divided by 2 into the right side and the right side values into the left side. Then here I am simplifying it. See, 1 minus 1 by 2 raised to the power n, I am putting in the left side. Taking 64 into the right side, so it will become 1 by 64. Then what is the denominator? 1 minus 1 by 2. 1 minus 1 by 2 is equal to 1 by 2. I am taking into the right side, so it will become 1 by 2. So here 1 minus 1 by 2 raised to the power n, which is equal to 255 divided by 2 into 1 by 2 into 1 by 64. You can simplify here this particular right hand side term. See here, I am multiplying 1 by 2 into 1 by 64, which is equal to 1 by 128. Then again we can multiply these two terms here. Then it will become 1 minus 1 by 2 raised to the power n, which is equal to 255 into 1, that is 255, 2 into 128, which is equal to 256. Now I am taking, see, 1 into the right side, or just rearranging it, this particular term. Then we can write 1 by 2 raised to the power n is equal to 1 minus 255 divided by 256. See here, we are taking the common denominator in the right hand side of the equation so that we can solve it and simplify accordingly. So 1 by 2 raised to the power n is equal to 1 by 256, because by taking the common denominator, then you are just multiplying and dividing here by 256. Then 256 minus 255, which is equal to 1. In denominator, we have a common denominator, that is 256. So which is equal to 1 by 256. Now I can write this 1 by 266 as a base of 2. See here, 1 by 2 raised to the power n is equal to, I can write it 1 by 2 raised to the power 8. So since we have a common base here, 1 by 2, n is equal to, then what is? It is 8. So 127, 1 by 2 is the n terms are there. N terms, that is 8 terms are there in the given series. Now, if you want to find out the sum of an infinite terms in the geometric progression, see, if the number of terms in the geometric progression is not finite, then the geometric progression is generally called, it is infinite geometric progression. And the formula to find the sum of infinite terms of a given geometric progression can be derived from the equation which we are used to find the sum of n terms in the finite geometric progression. See here, the sum we are already calculated here, that is by using this particular formula, that is a into 1 minus r raised to the power n divided by 1 minus r. See here, I am multiplying this particular terms, that is opening bracket by multiplying with a, then this equation will become, see, a into 1, that is a, minus a into r raised to the power n, that is a r raised to the power n, divided by 1 by r. Then I am dividing this particular equation into two parts, or splitting this equation into two parts, that is a divided by 1 minus r, then minus a r raised to the power n divided by 1 minus r. So if the number of terms are not finite, that is if n is approaches to infinite, that is n is infinitely large, then a raised to the power n by 1 minus r is also approaches to the 0. See, this is because as n increases indefinitely, then the value of r raised to the power n decreases, and then ar raised to the power n divided by 1 minus r, then which is approaches to 0. So the equation will remain as, see, this particular value will become 0. Then see here, what is remaining here? Then we have only the first term, that is a divided by 1 minus r. Since here the r is greater than minus 1 and less than 1. So here the sum of infinite term is equal to a divided by 1 minus r, where a is the first term and r is the common ratio. And this formula is actually shows that the sum of infinite terms in the geometric progression, which is equal to the first term divided by, first term, that is a divided by 1 minus common ratio. Now consider some example here. Find the sum of geometric series, that is 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. See here, the first term is equal to 1, that is a is equal to 1. R is equal to the ratio of two consecutive terms, that is 1 by 2 divided by 1. 1 by 2 divided by 1 we can rewrite through the cross multiplication, that is 1 by 2 into 1, which is equal to 1 by 2. So here the common ratio, that is R is equal to 1 by 2. And we know the sum of infinite term can be found out by using the equation, that is a divided by 1 minus r. So here a is equal to 1 and r is equal to 1 by 2. Then if you go for substituting all these values here, then it will become 1 by 1 minus 1 by 2, which we can write 1 minus 1 by 2, which is equal to 1 by 2. So it is 1 by 1 by 2, which is equal to 1 into cross multiplication, that is 2 by 1, which is equal to 1 into 2, which is equal to 2. So here the sum of the given geometric series is equal to 2. Similarly, we can also find the sum of given geometric progression, that is 1 by 3 plus 1 by 9 plus 1 by 27 up to infinite terms are there, and we want to find out the sum of this given geometric series. So of course it is an infinite GP, that is geometric progression, that is because here it is infinitely large. So here a is equal to 1 by 3, r is equal to the ratio of two consecutive terms, that is 1 by 9 divided by 1 by 3. We can rewrite this is by using the cross multiplication, which is 1 by 9 into 3 by 1, which is equal to 1 by 3. So here r is equal to, common ratio is equal to 1 by 3. Now we can use the formula for finding the sum of infinite terms in the geometric progression, that is a divided by 1 minus r. See, a is equal to 1 by 3 and r is equal to 1 by 3. So it is 1 by 3 divided by 1 minus 1 by 3. So which is equal to 1 by 3 divided by 1 minus 1 by 3, which is equal to 2 by 3. So we can do the cross multiplication here. 1 by 3 into 3 by 2, which is equal to 3 and 3 will be cancelled out. Then what is remaining here? 1 by 2. So here the sum of given geometric series is equal to 1 by 2. So let me conclude here. Today we have discussed what actually the geometric progression mean, and then we found how to find the n terms of a geometric progression and also the n terms of an sum of an n terms in a geometric progression along with some numerical examples. In the next lecture, we will discuss the simple and compound interest. See, we will see in the next lecture. Thank you.